Far beneath the Pacific Northwest, the region's most consequential hazard is proving to be less uniform, less predictable, and more geologically intricate than the broad public conversation usually suggests. How far offshore does the locked part of the Cascadia Subduction Zone really extend? Where is stress accumulating most efficiently? Where is it leaking away? And how much of the plate boundary is quietly being reorganized by fluids moving through deep faults? A new study highlighted in late February has sharpened those questions rather than settling them, and the implications reach well beyond academic mapping. The Cascadia margin is already known as one of North America's most serious earthquake sources, but the latest findings suggest that its internal architecture may influence how a future rupture spreads from segment to segment, and that possibility changes how the Pacific Northwest has to think about risk. The scale alone is enough to explain why any new detail matters. The Cascadia Subduction Zone stretches about 1,000 kilometers, or roughly 620 miles, from northern Vancouver Island to Cape Mendocino in California, where the Juan de Fuca Plate dives beneath the North American Plate. That slow collision is fed by new oceanic crust created at the Juan de Fuca Ridge, which moves outward, cools, becomes denser, and eventually sinks beneath the continent. The plates converge at roughly 4 centimeters a year, or about 1.6 inches a year, which is not fast in human terms, but is relentless in geologic terms. Over centuries, that steady motion loads the plate boundary with enough strain to produce giant earthquakes and tsunamis when the system fails. The Pacific Northwest sits atop a classic subduction environment, but Cascadia has its own particular geometry. The National Park Service describes the region as having two parallel mountain belts, the Coast Range near the coast and the Cascade Range farther inland. Between them lie broad lowlands, including the Willamette Valley in Oregon and Puget Sound in Washington. That topography is not incidental scenery, it is the surface expression of a plate boundary that is scraping, folding, heating, dewatering, and metamorphosing rock at different depths. Near the trench, sediment and pieces of hard crust are stripped from the descending plate and stacked into an accretionary wedge. Farther inland, the plate sinks to depths where hot fluids are released, helping generate the volcanic arc that includes Mount Rainier, Mount Hood, Mount Shasta, and other Cascade peaks. The landscape itself is a record of ongoing tectonic work. That geological framework is essential to understanding why the new research is important. The study described by phys.org and the University of Washington used a decade plus of seafloor monitoring to compare the behavior of different parts of the margin. It found a clear contrast between northern Cascadia, which behaved like a fully locked megathrust accumulating strain, and central Cascadia, where the data indicated a shallow slow slip event and later signs of fluid movement along faults. In the words of the research summary, other faults running roughly perpendicular to the subduction zone may act as pathways for trapped fluids to escape. That means the fault system is not just a smooth interface between two plates. It is a mechanically and hydrologically complex structure with separate zones of locking, creeping, slow slip, and fluid migration. The distinction between locked and slipping zones is not a technical footnote. In subduction systems, the locked portion is where stress accumulates over long periods because friction prevents the plates from sliding smoothly. When that stored energy is released, the result can be a megathrust earthquake. The National Park Service notes that giant earthquakes occur where the Juan de Fuca and North American plates are stuck together, and that these events can send tsunami waves across the coast if the seafloor uplifts or drops suddenly. PNSN similarly describes the Cascadia megathrust as a boundary with a locked zone, a transition zone where episodic tremor and slip occur, and deeper areas of more continuous movement. The latest study does not eliminate the danger of a great rupture. It refines the way scientists understand the distribution of that danger along the margin. To see why the geology matters, it helps to look at the basement under the forearc. Much of western Oregon, western Washington, and parts of Vancouver Island are underlain by Siletzia, a thick Paleogene oceanic basalt terrain that forms the basement of the Cascadia forearc. USGS work has shown that in southern Washington and northern Oregon, the Siletz terrain can be more than 20 kilometers thick and extends west of the coastline, making a steep contact with the offshore accreted sedimentary prism. In Washington, additional USGS modeling found that the terrain boundary coincides with a zone of seismic deformation and helps shape the way stress is distributed through the forearc. This matters because a subduction zone is not just a plate interface at depth, it is also a crustal edifice built on older blocks, terrains, and faults that can channel stress in unexpected ways. That forearc architecture helps explain why Cascadia varies so much along strike. A 2004 USGS professional paper on the Cascadia forearc of Washington found that the Juan de Fuca slab changes dip from about 2 to 7 degrees to around 12 degrees, where it encounters the thick Siletz terrain or related accreted crust. The same study identified a broad, possibly locked part of the interplate contact that may extend westward from about 25 kilometers depth beneath the coastline to as far as the deformation front, roughly 120 kilometers offshore. It also identified a separate crustal zone at the eastern boundary between the Siletz terrain and the Cascade Range, as a place that may concentrate future seismicity. In other words, the hazard is not a single line. It is a layered and segmented structural system that can focus strain in more than one place. This is one reason the new findings carry more weight than a simple, more or less hazard interpretation. The research highlighted in February emphasized variability in how earthquake energy may spread once rupture starts. Northern Cascadia appears to be holding strain in a comparatively rigid way. Central Cascadia, by contrast, appears to contain active channels for fluid release and shallow slow slip. That difference may affect whether a future earthquake moves through the margin as a relatively continuous break or encounters places where deformation is temporarily slowed, redistributed, or diverted. In a subduction zone, that kind of variability can influence shaking patterns, tsunami generation, and the extent to which different coastal segments are simultaneously involved. The fluid story is especially important because subduction zones do not only move rock, they move water. As the Juan de Fuca plate descends, heat and pressure drive water out of hydrated minerals and into surrounding rock. The National Park Service describes this as the plate reaching depths where it sweats hot water, and that water then contributes to magma generation in the volcanic arc. But water also affects fault strength. High pore fluid pressure can reduce friction, alter locking behavior, and encourage slow slip or tremor along parts of the plate interface. The new study's emphasis on seismic velocity changes linked to fluid dynamics fits squarely into this broader subduction zone physics. Dewatering, migration, trapping, and release can all influence how the margin behaves under strain. That is why the data from offshore observatories are so valuable. Most people think of Cascadia through the lens of onshore hazard maps and coastal tsunami scenarios, but the most important mechanics are offshore and buried. The University of Washington summary notes that the study drew on a long archive of seafloor measurements from stations off Vancouver Island in Oregon. Those observatories recorded subtle seismic noise signatures that researchers used to infer how the margin was moving beneath the ocean floor. The result was a more differentiated picture than the older assumption of a broad, relatively homogeneous locked zone. It is a reminder that the absence of frequent big earthquakes in the instrumental record does not mean the system is simple. It means the system is hard to observe directly, and the best clues often come from indirect signals. The geology of the coast itself also tells part of the story. The Cascadia margin is an accretionary margin, which means much of the sediment and crust on the incoming plate is scraped off and stacked at the edge of the continent rather than being subducted cleanly. Over geologic time, that process has built the Coast Range and Olympic Mountains out of ocean-derived material. NPS notes that tilted sandstone and shale layers in places like Olympic National Park record the enormous compression involved. This is not just scenery formed by uplift, it is a compressional wedge built by off-scraped marine sediment, basalt, and crustal fragments. Such a wedge can deform internally, host hidden faults, and interact with the underlying subduction interface, making the near-coastal portion of Cascadia structurally complicated even before one gets to the deeper plate boundary. Cascadia's volcanic arc is the other half of the regional tectonic system. Far inland, the descending slab reaches temperatures and pressures high enough to release fluids that promote melting in the mantle wedge, feeding volcanoes across the Cascade Range. The National Park Service notes that the arc includes Mount Rainier, Mount Hood, and Mount Shasta, and that these volcanoes mark where the subducting plate is deep enough to influence magma production. In geological terms, the Pacific Northwest is witnessing two linked systems at once: the shallow megathrust and forearc above, and the volcanic arc built by deeper subduction farther inland. The same subduction process that creates the giants of the coast also powers the Cascade volcano chain. That linkage makes the region unusually sensitive to changes in crustal architecture. The USGS forearc study found that the Silet's terrain and adjacent Cascade arc crust are not just passive blocks. Their boundaries coincide with zones of seismic deformation. The Mount St. Helens seismic zone, for example, aligns with the transition from Silet's crust into Cascade arc crust. That is an important clue, because it suggests that inherited crustal structure helps dictate where strain concentrates. The Pacific Northwest is not a blank plate boundary over which stress is spread evenly. It is a patchwork of terrains, accreted wedges, arc routes, and crustal boundaries that can each alter the path of deformation. Even the thickness of the forearc varies enough to matter. USGS data indicate that beneath the Oregon Coast Range, the accreted terrain can be 25 to 35 kilometers thick, whereas offshore Vancouver Island it may be only about 6 kilometers thick. Such a difference changes how the plate boundary is loaded, how fluids are expelled, and how the upper plate responds mechanically. A thicker forearc can behave differently from a thinner one, especially when it is built from different terrains and intersected by major faults. This helps explain why the Cascadia margin does not respond uniformly from south to north, and why researchers continue to find along strike differences in seismicity, accretionary prism width, and volcanic production. Those along strike differences are central to the current warning. The February study's northern and central observations fit into a wider pattern already documented by earlier work on slow slip and tremor. Cascadia is unusual among subduction zones because it hosts recurring episodic tremor and slip deep along the plate interface, while the shallow locked portion can still accumulate enormous strain. USGS reviews of slow slip phenomena describe this motion as evolving more slowly and over longer durations than a normal earthquake, often between the 30 and 40 kilometer depth contours, where observation was historically difficult. That means the deep part of the system can relieve stress in a quiet way, while the shallow part remains primed for a much larger release. The new offshore results sharpen that contrast rather than simplifying it. The possibility that faults perpendicular to the subduction zone may act as fluid highways introduces another layer of complexity. Faults in the overriding plate can either help drain pressure or partition deformation in ways that affect how the megathrust behaves. The 2026 study summary says velocity changes between 2017 and 2022 were tied to fluid dynamics and that these perpendicular faults may let trapped fluid escape. That is not a trivial detail. In rock mechanics, the presence or absence of fluid can change effective stress, alter friction, and influence whether a locked patch fails suddenly or creeps in a more distributed way. In a system the size of Cascadia, those effects can accumulate over many kilometers and change the eventual rupture pattern. The hazard history of the region makes that even more significant. USGS and state sources say Cascadia has experienced numerous great earthquakes over the Holocene, with at least 19 megathrust events in the past 10,000 years, and an average recurrence interval on the order of 500 to 660 years, though the spacing is irregular. The last great rupture occurred in 1700. That means the region has already demonstrated the ability to produce enormous coast-wide earthquakes, and there is no reason to assume future behavior will be gentle, simply because the margin has been relatively quiet in recorded history. Quiet subduction zones are often the ones that build the most misleading sense of stability. The geological record offshore has become an increasingly important tool for understanding that past. USGS work in early 2026 reported widespread abyssal landslides tied to Cascadia earthquakes, adding another line of evidence that ancient Great Quakes left signatures deep on the seafloor. Such evidence matters because it helps reconstruct how often rupture happened, how far it spread, and what kinds of slope failure accompanied it. The broader point is that Cascadia's hazard is written not only in faults and volcanoes, but also in sediment layers, underwater landslides, uplifted shorelines, and ghost forests along the coast. Each clue adds to the picture of a margin capable of large, repeated, destructive events. The new study fits into that larger field of evidence by showing that the present-day stress field is not distributed evenly. The central Cascadia segment appears to be shaped by fluid migration and shallow slow slip, while the northern segment looks more locked and stress-loaded. That does not mean one part is safe and the other is dangerous. It means each part may contribute differently to a future rupture. A fault that is more locked may store more stress. A fault with more fluid pathways may alter how rupture propagates. A fault with complicated crustal boundaries may concentrate deformation at its edges. Taken together, those factors suggest that the Pacific Northwest may face a hazard profile that is both broader and more internally varied than a single headline number can capture. For communities across the region, the practical meaning is straightforward, even if the geology is not. Infrastructure built in the lowlands between the Coast Range and Cascades sits in a tectonic basin shaped by the same forces that could produce severe shaking and coastal inundation. Highway corridors, ports, bridges, pipelines, water systems, and older buildings all sit within a landscape built by subduction and still being deformed by it. In Oregon, the Willamette Valley lies between the ranges that mark the subduction system. In Washington, Puget Sound occupies a similar low area. Those broad lowlands are economically vital, but they are also geologically young and tectonically active. The new study does not change that reality. It simply makes the underlying machinery more visible. What stands out most in the current work is the way it bridges scales. At one end are tiny changes in seismic velocity measured by instruments on the seafloor. At the other end are continent scale effects: mountain building, volcanic arc formation, great earthquakes, tsunamis, and the long-term evolution of the Pacific Northwest. Between those scales sit terrains like siletzia, accretionary wedges, shallow, slow slip zones, deep fluid release, and faults that may channel stress in ways that are only now becoming clear. Cascadia is not simply one hazard layered on top of a beautiful landscape. It is the process that built that landscape, and it is still at work beneath it. The result is a threat that is larger than the average resident can see, and more structurally complex than old simplified models suggested. The fault offshore is long, the forearc is thick in some places and thin in others. The accreted crust varies in character along strike. The volcanic arc reflects deep dehydration and melting, and the shallow plate boundary is not behaving identically from north to south. A megathrust earthquake remains the defining danger, but the new science indicates that its rupture path may be shaped by a web of geology already in place beneath the seafloor and beneath the coast. In a region where the ground has been moving for millions of years and will continue to move long after any single quake is forgotten, that deeper geological understanding is not a side note. It is the main event.